So what I would like to do now is just go over a couple examples utilizing Kirchhoff's laws. So what I'd like to do is I've got two circuits. I've got one here and then I've got another one here. And both of these are actually sort of combinations of both parallel and series circuits. And I would like to find the current and the voltage on each of these resistors. So as a starting point, let's just kind of talk about what's going on here. So the junction rule tells me that, well, whatever the current is, right, current's going to flow out of the positive side, and we use the long side of the battery to be the positive side. So that would be the positive side right there. Now, conventional current is going to flow out of the positive side of that battery, and it's going to split here and here. So I know whatever the current is right there, the current here and here should sum to it. So I know that I1 is going to equal I2 plus I3. Now in terms of voltage, well, there's really two different loops I can make through this circuit. There's one loop right here, and there's another loop right there. So the battery gives it 10 volts here, which means we have to have a 10 volt drop over this resistor, because there's no other resistors to lose voltage over. So I know that this is going to be 10 volts. Similarly, I know that this is a 10 volt gain. I know I'm going to have a 10 volt drop over those combined here as well. So I know this is going to be 10 volts, and I don't know what each of these are, but I know that they're going to sum up to 10 volts. So I think what I might do now is just kind of start off by making a little box for organizing my what I know. So, and these are pretty common to use when you're solving circuits. So we can just set up a little box and label it. Let's just say R, V, and I. Okay, and my resistors are 5 ohms, 3 ohms, and 8 ohms. And I know right away that the 5 ohm resistor, like I just said, has to be 10 volts. So now when it comes to I for that, we can actually calculate it straight away, right? I can use Ohm's law and apply it just over this resistor right here. So let's go ahead and do that, right? I for that resistor should be V over R, right? I'm just applying Ohm's law, V equals IR. I is V over R. So I'm going to get 2 amps for that resistor. So I've pretty much, right, I've already figured out everything for this resistor over on the left, right? That I right there. That is 2 amps. Now, let's think about the other two. So I don't know the current in either of the other two resistors. I know their voltage has to sum up to 10. So what I'm going to do now, and this is something that's a pretty common approach, is I'm going to find the equivalent resistance of the circuit, and I'm going to use that to help me out. So I know that I don't really have just a parallel or a series circuit. Instead, I've got sort of a combo. So what I'm going to have to do here is I'm going to have to add in parallel, but those two are in series, right? So what I'm doing is I'm sort of treating these like they're in series with each other. That's why I'm adding them the regular way here. And then I'm adding that combo in parallel with this to find the equivalent resistance of the whole circuit. Okay, so when I work this out, I'm getting, and I'm going to drop my units right now, 1 over 11. So REQ should be 1 over 5 plus 1 over 11. And then take the reciprocal. I'm going to go ahead and do that in my calculator over here. You guys can't see my calculator, but that's fine. And then okay, so I'm getting an equivalent resistance of about 3.4 2.4 ohms. So that's the resistance of the whole circuit, all the resistors taken together. So we're basically modeling the circuit just like this, right, where this is really the resistance of all three of those together, and that's equal to 3.44 ohms. Maybe I'll pull that out of the way just so that I'm working with some semblance of order here. I know that this voltage is 10 volts, so I can find the current flowing through the total circuit, right? In my first diagram, that's what I called I1. So in order to do that, right, again, I just do I equals V over R, but now I'm modeling all of the resistors, and the voltage drop across all of them is 10 volts, right? It doesn't matter if I go this way, or I go that way, or I sort of think of them all as one. It's a 10 volt drop. So I would do 10 volts over 3.44 ohms, and that gets me, oops, 2.91 amps. 2.91 amps. So this I1 up here, right there, that's 2.91 amps. All right. Now, I1 isn't actually the current through any of my resistors, but I know that I3, right, that's the current right here, right, this goes through both of these two. I know that these should sum up to I1, right? In other words, I can say that I1, right, I wrote this equation before, I1 should equal I2 plus I3, and I know that I2 is 2 amps. So if I solve this for I3, right, I get that. I3 is equal to 0.91 amps. So I'm going to go ahead and put that in my table here. That should be both of them, right, because of the junction rule, right? However much current goes through one of these, it has to go through the other one. And now to find V for both of these, I can just do I times R. So for this first one, I can do 0.91 times 3, and that gets me 2.73 volts. And then I can also multiply these to get V here, right? Again, I'm just using Ohm's law. I times R should give me V. 0.91 times 8. And that gets me 7.28 volts. Now, let's notice the loop rule here as well, right? So for this 3 ohm resistor, I'm getting 2.73 volts. Maybe I'll just sort of write that right here. And for the 8 ohm resistor, I've got 7.28 volts. And notice that these two should be summing, these two should sum to 10 volts, right? Because the voltage drop across both of those should be 10. Now, I'm not getting it exactly right. I'm off by like 1 decimal place, and that's because I rounded a little bit earlier. So I hope this was helpful. I hope this kind of showed how we can apply Kirchhoff's laws to solving something like this. And now let's do one more. So on this page here, let's do the same exact thing. So this is a little bit trickier because for this one, I can't really see anything right away. So if I think about the junction rule, right, the junction rule tells me whatever the current is flowing through here, here plus here, those currents should sum to whatever this current is. The loop rule tells me that I should have a full 15 volt drop if I go through both of these, or if I go through both of these. So I don't have any resistors that are just simply in parallel with the battery, so this is a little more complicated. So I think as a starting point, well, let me make my table as a starting point. V, I, R. But I think the first thing I'm going to do now is I'm actually going to do equivalent resistance of this circuit. So what I've got here is I've got this, and this is in series with these two in parallel. So first I have to combine these in parallel and then add them actually in series with this one. So that would look something like this for the whole circuit, right? So we're doing series addition, which is 20 ohms, but I also have to add these two combined with that one. So we're doing regular addition for this plus these, but these are in parallel, so I have to actually add them like this. And then I have to take the reciprocal. It'll look like that, right? And that's because here, right, 1 over the equivalent resistance of those would equal 1 over 12 plus 1 over 6. And then to just get the equivalent resistance of these two, right, I actually have to end, whatever this result is, I need to take the reciprocal of that in order to get this REQ and put that here. So that's kind of why it looks like this. Okay, so now I'm going to go ahead and try to just kind of work this out in my calculator. Maybe I'll just add the first two that are in parallel to begin with. So that's 1 over 12 plus 1 over 6. And then take the reciprocal of that. And I actually get 4 ohms, which is nice. So this tells me that the equivalent resistance of the whole circuit is 24 ohms. Nice. So now if I think of the whole circuit as just kind of one thing, right? So I model the circuit. Maybe I'll shrink this a little bit, get it out of the way. Okay, so if I model the circuit as just this, right, this is 15 volts, and then REQ is 24 ohms. Well, we can calculate the total current in the circuit using Ohm's law, right? V equals IR, or I equals V over R. And if I do that, I get 0.625 amps. That's the total current. So that tells me that the total current flowing in the circuit, that would be the current here, that would be the current also here, right? That is 0.625 amps. Now notice that that's the current that's going through this resistor right here, the 20 ohm resistor. And I forgot to label this table. Maybe I'll do that really quick. Oh, and I'm doing it in a different order than I did in the last table. I hope that's not too confusing. So in the 20 ohm resistor, I've got 0.625 amps, just like that. Now if I want to find the voltage through that resistor, right, I've got I and R, so now I can find the V. So I just do I times 20, and that's giving me a voltage of 12.5 volts right there. And now let's take a look at the loop rule, right? I know that if this is 12.5 volts, well, that actually tells me right away what these have to be. Because if I imagine our loops, right, we've got actually two possible loops we can make. This is a 15 volt gain, a 12.5 volt drop. Well, we have to lose such an amount here so that the total that we lose is 15 volts. So if I go around this loop, I lose 12.5. The only way that I can get a total drop of 15 is if this is a 2.5 volt drop. And it's the same thing over here as well on this resistor, right? Because you lose 12.5, you have to lose 2.5 to lose 15 total. Same thing if you go this way, you lose 12.5 here, you have to lose 2.5 again in order to lose 15 total. So I can say right away that these are both going to be 2.5 volts and 2.5 volts. And now that I want to find these currents, I can just do I equals V over R for each of them respectively. So let's do 2.5 over 12, and that gets me 0.208 amps. And then for this one, let's do 2.5 over 6, and that gets me 0.42 about amps. And now we can actually check that the junction rule is working, right? Because the total current that's flowing here should equal the sum of the current here and here. So if we sum this and this, we should actually get this. And we can see that it just about does. Again, it's off at the third decimal place, probably just because of rounding. But if we do this plus this, we do indeed get that, because the current here plus here should equal the current there, right? This is our junction right here, right? The current going in here splits to be here and here. So, right, this is like 0.208 amps of current here. This is 0.42 amps of current there. And those both sum up right about to this value here. Oh, geez. Oh, geez. Did not mean to do that. But yeah, they both sum up to this value here. All right, so the junction rule is being satisfied. All right, I hope this was helpful.